Namaste, hello everyone, welcome to this session. So, in this session we are going to solve some examples on the topics we studied in the lectures 20 to 22 of this course on experimental model analysis. The topics we covered in these lectures are principle of experimental model analysis, excitation using an impact hammer and response measurement and piezoelectric accelerometer. So, we have several multiple choice questions, short answer questions in the assignments, right. But in this session we are going to solve two examples which I have designed to addressing some of the concepts we have studied in these lectures. So, please watch these lectures to know the background theory of these examples. Let us get started with example number 1. So, let me write the question first. Question: impact hammer and a piezoelectric accelerometer are used for FRF measurement on a structure. Their sensitivities are 40 millivolt per Newton and 0.5 volt per G respectively. At a certain frequency, the amplitudes of the measured force and acceleration signals are 0.6 volt and 800 millivolt respectively. Find the values of force, acceleration and inertance FRF. Also find FRF magnitude in dB. Okay. So, this is basically the problem. So, here an impact hammer and accelerometer are used to measure the FRF, and we have been given the sensitivities of both these, and also at a certain harmonic frequency omega, right. What are the amplitudes of the measured force and acceleration signals, those are given, and you have been asked to find what is the magnitude of the force, the physical value of the force in inching units and acceleration signal and the FRF, correct. The values given are in terms of electrical quantities, we have to find them in terms of the inching units, the corresponding SI units. Let us start solving this. So, solution. So, therefore, what quantities are given to us? Given, if you talk in terms of force, then for the force, the measured voltage, if I call this as Vf, that is given as 0.6, right, 0.6 volts, correct, and the sensitivity if I call as SF, then that is given as 40 millivolt per Newton, and for acceleration we have been given the voltage which I can call as VA, voltage corresponding acceleration, that is given as 800 millivolts, and sensitivity which I can call as SA, it is given as 0.5 volt per G. So, these quantities are given to us, and now we have to basically find out the force first. So, let us do that. So, if I say the force, then the force F will be equal to the whatever is the voltage Vf divided by the sensitivity of the force transfer Sf upon Vf, correct, that will give me the force in newtons. So, if I substitute these values here, now while using these values I must be careful in using the correct units, right. So, that care should be taken. So, in this case voltage is 0.6, so I substitute right 0.6 here. Now, SF is in terms of millivolts, so I must convert it to the volts, right, in order to get the correct value of the force in newtons. So, then because we know that the 1 millivolt 1 volt actually is equal to 1000 millivolts, is not it, 1 volt is equal to 1000 millivolts. So, 40 upon 1000 I will do, that will give me the sensitivity in terms of the volt per Newton, and then if I do this sum, so this basically gives me 15 newtons. So, it means that the force that has been measured as 0.6 volt, it corresponds to 15 newtons of force, correct. Now, we can talk about finding the acceleration. Let us say acceleration is, if I call this as A, right, acceleration, right, and so A will be equal to, now in the same way, voltage of the acceleration divided by the sensitivity of the accelerometer. Here also I should be careful with the units. The voltage has been given as 800 millivolts. So, let us convert it to volt first. So, 800 divided by 1000, and then the sensitivity is in terms of the 0.5 volt per G, right. So, I would like to have acceleration in terms of meter per second square, right. So, I should convert this to sensitivity in terms of volt per meter per second square, correct. So, therefore, I will divide this by 9.8, because the 1 G is equal to 9.8 meter per second square, and now if I work out this number, this terms comes around 15.68 meter per second square. So, it means that 18 millivolts of voltage which we have got from the accelerometer, that corresponds to 15.68 meter per second square. So, that completes our calculation of acceleration, and the last thing is now inertance FRF. Now, the inertance FRF, of course, this is at the frequency at omega, where we have got the corresponding to the acceleration and force signal. So, therefore, if we represent it by say alpha I just for inertance, then we can write that as the A, and this is at this we have got at frequency omega. So, I will say omega, and the force we have measured, that also corresponds to frequency omega. So, that is how I will write A of omega upon F of omega. So, A of omega is 15.68 divided by 15, correct. So, that gives comes around 1.0453 meter per second square per Newton, right. That is the unit of the inertance FRF. So, the value is 1.0453 meter per second square per Newton. Now, in dB, if I wish to find, then I can convert this absolute value into dB, right, and the dB in alpha I in dB will be equal to 20 log 10 alpha I divided by the reference value, which I would take by default as 1, right. And if I compute this quantity, this comes around 0.3851 dB, right. So, that gives us the FRF in dB. So in this way I think we have completed the solution of example number 1, right. Let us go to next page and start with example number 2. Let me write the question first. An accelerometer with properties m is equal to 20 grams, k is equal to 2.85 into 10 to the power 7 Newton per meter, and viscous damping coefficient 135.71 Newton second per meter is used to measure acceleration of a structure, right. If the relative displacement of the seismic mass of the accelerometer is 6.2 into 10 to the power minus 9 meters, find the acceleration of the structure in meter per second square, right. So, this is the problem, right. So, here essentially a accelerometer is used and mounted on the structure, and the properties of accelerometer are given to us, and also given to us is that if the relative displacement of the seismic mass of the accelerometer with respect to the structure, if that relative displacement is 6.2 in 10 to the power minus 7 minus 9, then what is the acceleration of the structure on which the accelerometer is mounted? That is the question, right. So, I think maybe this we have studied the theory of this in the lecture classes, and right. So, but then just for the benefit of all, I am just giving a summary of what is the principle of this measurement and how we are going to estimate the value of the acceleration, right. So, just background theory, okay. It is just a brief review. So, essentially what is there is that we have this accelerometer, in this form. We have this accelerometer like this. Just I am making a very simple sketch for a quick explanation. Like this, okay. So, this is the body of the accelerometer, and then inside this body we have this the mass, seismic mass like this, right. And then we have the piezo disc like this. So, this is the piezo disc, okay, and this is the seismic mass, okay. And then, so maybe I can write here seismic mass and piezo disc. Okay. And now this structure is this accelerometer is mounted on the structure whose acceleration you want to measure. It is mounted on the structure whose acceleration you want to measure. Let us say this is the structure. Right, and then of course some stud or something, or maybe magnetic mounting, or some glue may be used. All that we have discussed in the lecture, how accelerometers are mounted. Maybe we have used a stud like this. This is mounted, right, and this is the accelerometer, and then this is the structure whose acceleration is to be measured. And now for the purpose of analysis, this can be approximated like a single degree of freedom system, which means if this again, if I draw the structure like this, then we can approximate this by single degree of freedom system. We can have a again seismic mass, and the piezo disc, it will have some stiffness damping. So and then there will be some stiffness also coming from the some decompression spring that is used in the accelerometer, but that we can ignore for the present discussion, and we can just say that this is the stiffness and this is the damping of the piezo disc. So now this structure, let us say if the acceleration of this structure is this, why not let us say sin omega t, then what is going to happen? When this accelerometer vibrates along because of the structure, the seismic mass is going to vibrate, and if we call the vibration of the seismic mass as being given by x of t, right, then we can talk in terms of the relative displacement. Relative displacement of the seismic mass with respect to the structure. That is very important, z, and that can be written as x minus y. So why that is important? Because the piezo disc, which is the active element here, right, and what is going to happen? The displacement of the piezo disc, or the compression or the extension of the piezo disc is basically z, the movement, the relative displacement of its top surface and the bottom surface. So z is the defines the compression or the extension of the piezo disc, and that would determine how much electric charge it generates, and that charge we measure outside and then interpret it in terms of the acceleration. That is essentially the principle of measurement of acceleration using the piezoelectric accelerometer. So if this z is given, which is basically the will be in some way proportional to the charge we get, then the question is how much that charge corresponds to the acceleration, correct? So in the theory class, then we have discussed the further analysis of all this, and we got the result that this z upon y, right, this z is actually equal to at a particular frequency, this is at particular frequency, this is equal to omega upon omega n square y, okay. So remember, this is at a certain omega is equal to 1 minus omega upon omega n whole square plus 2 zeta omega upon omega n whole square. This is the expression we got, and we also discussed in the lecture classes that an accelerometer has to satisfy the condition that its natural frequency must be much larger than the frequency for which you are trying to measure the acceleration, right. So for an accelerometer, omega n, the natural frequency of the accelerometer should be much larger than the frequency omega, right corresponding to the excitation, right, for which it is trying to measure the acceleration, and omega n is the natural frequency of the accelerometer, not of the structure. Okay. So, when that is the case, as we discussed and demonstrated in the lecture classes, that this z then would be approximately equal to omega upon omega n whole square into y, because denominator will be almost equal to 1. And if that is so, then what is going to happen, that we will have this means that we will have the omega square into y is equal to omega n square into z, right. And what is omega square y? Because if y is equal to y naught sin omega t is the acceleration, the y naught into y into omega square is actually equal to the acceleration. It is actually the acceleration signal. So, it means that this is nothing but the acceleration A of the structure, right, and this will be equal to omega n square z. So, it means if I have this measurement z, then if I multiply it by omega n square, I essentially get the acceleration of the structure. Of course, that is valid for the condition that the accelerometer must satisfy that its omega n is much larger than omega n. So, in that frequency range, this interpretation would be valid, right. You need to multiply z, the output of the accelerometer, with omega n square, and you get the acceleration of the structure, provided this condition is satisfied. The accelerometers are designed to have a high natural frequency, so that we have a reasonable frequency range over which measurement of acceleration can be made. Let us now determine the acceleration for the present case. So, essentially this is the theory, this is the background theory, and this final expression I have shown, A is equal to omega n square z, that is the only one we need to use in the present example, right. We do not have to derive everything, right. So, let us make use of this expression to find the acceleration. Let us go to next page, and for the present example, now let us determine the natural frequency, the natural frequency of the accelerometer, which is very easy. We know that it is acting like a single degree of freedom system. So, omega n is equal to under root k by m, right, and we have been given the value of k and m. So, we can just substitute that here, 2.85 into 10 to the power 7 divided by 20 grams. So, convert it to kg. So, always while solving problems, you should be mindful of the units. Always make it a rule that you always use SI units for all the variables. So, convert them appropriately, right. So, this gives us 3.76 into 10 to the power 4 radians per second. So, that is the natural frequency of the accelerometer, right, and therefore, the acceleration would be therefore, the acceleration of the structure A would be equal to omega n square z, which means 3.76 into 10 to the power 4 square multiplied by 6.2 into 10 to the power minus 9 meters, and that gives me around 8.82 meter per second square. So, that is nothing but the acceleration of the structure. So, that is how the accelerometer can be used to measure the acceleration of the structure. So, in this way you can see we have solved these two numerical examples based on the lectures 20 to 22, right. So, I think now we can stop here. Dhanyavad. Thank you.